Hello everyone, this is the solution to example 11 on rotated vessels. So here is the problem. A cylindrical tank shown, which is filled with water, is rotated about its vertical axis. Compute the maximum pressure that can develop for the following angular speeds: 60 revolutions per minute, 120 revolutions per minute, and 240 revolutions per minute. So this is the given figure. For part A, let's compute for the height of the parabolic surface that will form. By the way, if you look at the details of the tank, there is an opening at the center, so therefore the airspace here will be 0 initially. The air pressure is 0. So H1 is 0.005589, omega square, radius is zero point 0.3. So H1 is 0.1811 meter, which is less than 2 times zero point 0.3, the maximum height of parabolic surface that will reach the top rim. But in this case, it is only 0.1811, so the parabolic surface will be as shown. That's only that. Then, because the parabolic surface is inside the parent cylinder, then from this horizontal line, distance up to the leftmost or outermost surface is half of the height, and also from horizontal to vertex, half of the height. So 0.1811 must be divided by 2. The maximum pressure occurs at the periphery on the bottom, intersection between the walls and the bottom. So it is either here, sa front, the rearmost point, or the leftmost point. So let's consider the leftmost point because it's the same. So therefore, the pressure is gamma times h, gamma specific weight of water times 8h, and the depth is, because this is zero pressure, the h is 0.6 plus 0.1811 over 2. So 9.81 times 0.6 plus 0.1811 over 2, and that would be equal to 6.774 kilopascals. For the second question, let's solve for H2. So H2 is 0.0005589120 square times 0 0.3 square, and it is equal to 0.7243 meter, which is this time greater than 2 times 0 0.3. So that means, and it is less than this height here, so therefore we are sure that the vortex is still within the tank, but it will extend up, it will cross the top cover as shown in the figure. So this time, the principle that we have to divide it by 2 is no longer applicable because the parabolic surface extends beyond the parent cylinder. Now, to solve for the height of, so this is 0.7243, the height of the parabolic surface inside the parent cylinder, I derive a formula for that on the lecture video, which I uploaded on rotated vessel. So the formula is square root of 2kh in general, where h is 0.7243 and k is the empty depth of the tank, which is 0.3. So you look at the derivation there. So I'll call that y2. That formula for y2 or y in general is square root of 2kh. So substitute square root of 2 times 0.3 times 0.7243. So y2 is 0.6592 meters. By the way, this formula was derived in my lecture video on rotated vessels by the following manner. You have to apply squared property of parabola. You denote this with another radius. So y2, for example, y2 as to this radius square equals h as to r squared. Then the second equation would be based on volume of air inside the parent cylinder, which is pi radius of this circle, let's say r2 square, pi over 2 r2 square times y2 to the original volume pi r square k, so that you can derive this formula. Having found y2, then we can compute this depth from the vortex to bottom equal to 0.9, 0.6 plus 0.3 minus 0.7, 0.9 minus y2 rather. That's why you get 0.2408. Therefore, the distance from zero pressure top up to here is 0.7243 plus 0.248. So the pressure is 9.81 times quantity 0.7243 plus 0.2408. So you'll get 9.467 kilopascals. Again, the 0.2408 meter is 0.9 minus y2. Then for the third case, H3 is equal to 0.00005589, 240 square, 0.3 square, and that is equal to 2.897. Then let's compare this value to HV, the height of or the height or the parabolic surface that will form such that its vortex will exactly form on the bottom center, which is given by capital H square over 2K, which I also derived in my lecture video on rotated vessels. You look at the derivation there. That's why I want you to look at the lecture video first before proceeding to the example so that there will be no more questions anymore. So height is 0.9, then K is 0.3, and that will be equal to 1.35 meter only. So therefore, because this is 2.897 greater than 1.35, the vortex will extend beyond the bottom center, and it looks like that. So this is the surface with overall height 2.897 meter. So what is important here is we need to compute this distance from the bottom center to the vortex so that we can compute this distance, which is 2.897 minus this distance. I will call this distance y3, this radius r3, and the intersection of the surface with the top cover as r4. Then apply squared property of parabola. Y3 as to r3 square equals y3 plus height 0.9 as to r4 square equals 2.897 height of paraboloid of revolution times radius of paraboloid 0.3 square. So from here we can express r3 square in terms of y3. r3 square is 0.3 square y3 over 2.897, while r4 square is equal to 0.3 square times the quantity y3 plus 0.9 over 2.897. So what's next is we reinforce the volume of air inside the parent right circular cylinder to be equal to the original volume of air because no air has escaped here. The volume of air initial and final is the same. In the same manner, the volume of liquid initial and final is the same, but we will use volume of air instead. Air is represented by this paraboloid of revolution with two bases, and the formula for volume is pi over 2 quantity r3 square plus r4 square times quantity h, which is 0.9, equals pi 0.3 square times k 0.3. So the analysis is volume of air final equals volume of air initial. Cancelling out pi, then we have r3 square plus r4 square close times 0.9 equals 2 times 0.3 square times 0.3. Replacing r3 square by 0.3 square y3 over 2.897, r4 square by 0.3 square times quantity y3 plus 0.9 over 2.897, close times 0.9 equals 2 times 0.3 square times 0.3, cancelling out 0.3 square, cross multiply 2.897, then we'll have y3 plus 0.9 close equals 2 times 2.897 times 0.3 over 0.9 after cancelling out 0.3 square. Then we can now solve y3. y3 is 0.5157 meter. Finally, the pressure maximum here is equal to 9.81 times quantity 2.897 height of paraboloid minus y3. So 9.81 times quantity 2.897 minus y3, 0.5157. So the maximum pressure is equal to 23.36 kilopascals. So that's all for this video.